Let's discuss functions. The notation to define a function is t takes Rn to Rm. The function is named t. It takes vectors from Rn and turns them into vectors in Rm. In other words, this is the input and this is the output. For the CS people, here's a Java type signature of t. Here's an example. Let t take R2 to R3 be given by t of x1, x2 equals x1, 1, x2. Notice inside of t is a vector from R2, and it's returning a vector in R3. The x1 and x2 are just variables or placeholders. T of 2, 3 equals 2, 1, 3. Look at where the 2 and the 3 come from and where they go, and compare that to x1 and x2. The image of a function is all the points hit by the function. More specifically, a point y in Rm is in the image of t if there is an x in Rn, so that t of x equals y. We're going to encounter this quite a bit. For now, it'll be useful to know it's a thing. Is the vector 3, 1, 4 in the image of t from before? Yes, it is. T of 3, 4 equals 3, 1, 4. How about the vector 2, 0, 2? No. Everything in the image of t must have a 1 in the second coordinate. 2, 0, 2 does not. In linear algebra, there is one very special type of function called a linear transformation. A linear transformation t takes Rn to Rm is a function so that 1, t of u plus v equals t of u plus t of v for all u and v in Rn, and 2, t of c times v equals c times t of v for all scalars c and v in Rn. This says it doesn't matter if you add vectors or multiply them by a scalar before or after you apply the function. A linear transformation preserves these operations. This will turn out to be essential when we're talking about more abstract vector spaces, but that's the future. Let t take R2 to R3 be given, and t of x1, x2 equal x1, 0, x2. Is t a linear transformation? Hi, I'm going to say something that's going to scare you. We're going to need to write a proof for this. Oh, hey. It's going to be okay. We're going to walk through this example, and other examples will be similar. Linear algebra is a proof course. Oh, there you are. I've been looking all over. Now, it's going to be okay. We're going to do this example, and then you're going to have time to practice. Are you ready? Because you don't have a choice. To prove this, we need to show the two conditions. For the first one, write t of x1, x2 plus y1, y2. We are picking two vectors in R2 and adding them together. Add these vectors inside of t. Now apply t to this sum. We have x1 plus y1, 0, x2 plus y2. At this point, after we've applied our function, move to the other side of the equation. Start directly below the other one. T of x1, x2 plus t of y1, y2. Apply t to each of these and add the results. Notice we get the same as we did on the line above. This is what we wanted, and it shows the first condition. The scalar multiple is similar. Start with t of c times x1, x2, push the c inside the vector, and apply t. Do the other side of the equation, c times t of x1, x2, apply t, and push c inside. Again, we get the same thing. Therefore, t is a linear transformation. But this looks ugly. Let's rewrite this so we look really smart. Basically, we're going to rewrite each part, except in a single line from beginning to end. This way it looks like we knew exactly what we were doing the whole time. When you're finished, don't forget to conclude with, so t is a linear transformation. It ties the proof together and shows that you knew what you wanted to do. Here's one last example. Is t of x1, x2 equals x1, 1, x2 a linear transformation? Well, this looks virtually identical to the previous problem. Let's just do it the exact same way. T of x1, x2 plus y1, y2. Combine the inside and apply t. Do the other side, t of x1, x2 plus t of y1, y2. Apply t and add. Oh no, we don't get the same thing. The middle coordinates are different. I guess that means t is not linear.